Alright, so we're going to talk about p-values, which is like the most important number you need to find. Put the computers away, please. So, p-value is what we use to make decisions. We compare this to alpha. Make decisions. If p-value is less than alpha, you reject H naught. So, the technical definition is up here. It's the probability that an observed value could happen by random chance if H naught is true. So that it's not perfect, but if you think about the p-value as the probability that they're telling the truth, it's not like the perfect way, but it's close enough to help you make decisions. So you can get this little graph here. The p-value is a little teeny tiny area on one side or the other. The smaller that area is, that means the further we are away from the middle, and the more likely we are to call the original claim a cap, if you will. So smaller p-values mean any of these things. Results far away from what we expected, results that are very unlikely, less likely that HO is true, we're more likely to reject HO, we are further into the tail. So we gotta know how to find it. So to find the p-value, you always go toward the tail, and there's kind of 4 different situations that come up. This is your general formula, and this is just supposed to represent like a number line. Just adding in the negative 999 is over there, and then 999 is over there. So if the HA is U is greater, mu is greater than, we think that something is higher than the original claim. This is the situation. You have an alpha over here. You would have a positive t value, so t would also be somewhere over here. And then to find the p-value, you would do TCDF, t comma 99999. Degrees of freedom. And that would give you your answer. So for example, let's assume U is a greater than situation and T equals 2.5 and N equals 41. Like that's enough information for you to find the p-value. You have to know how to do it from that. So what I would do is go to TCDF. Greater than means I'm looking like all the way to the right hand tail. value is 2.5, which is like here-ish. But I want to know the probability it's above that. So don't I want to go from 2.5 to 99999? 2.5. And then the degrees of freedom is what? 40. So type that in and let's make sure we all get the same thing. So I got 0.008. Double check, make sure you get that too. Yep. One zero zero eight. Okay. Let's say alpha was 0.05. Would I reject H naught? So this is like where you start to make decisions. If alpha is 0.05 in this scenario, you reject this is the probability that the original claim is true. Basically. It's not perfect, but that's a really low probability. That means we're really far into the tail. Like there's not much area left. So it's a very small number, which means it's a very unlikely situation that the original claim is true. So what you do is compare to alpha. If this number is smaller than alpha, this is your cutoff point. If this number is smaller, we reject the original claim. So are we rejecting the original claim here? Yes, because this number is smaller than alpha. Right. So that's how you decide. You look at the p-value you get, you compare it to their alpha. Alright, if HA is used less than, kind of flips around. So you'd be on the left hand side. And I go towards the tail. So I want to look like in this part over here. So I'm going to have a negative t value. And I want to know the probability that we're lower than that. Like to the left, toward the tail, toward the extremes. So you are going to go TCF negative 9999, comma T, comma degrees of freedom. So it flips from the previous one. So let's say mu is less than. So we're looking for the lower end, the lower tail. Let's say T is negative 1.5 and N is 50. Find the p. Question? I got 0.07. Agree? We get 0.07? Alright, let's say alpha was 0.10. What would we do with HO? Reject it or fail to reject it? We reject it. Why? Because this p-value is smaller. But let's say alpha was 0.05. Would we reject HO or fail to reject it? Fail to reject it because the p-value is bigger. But again, that's how you make your decisions. This is like the key number to make decisions. Questions on either of those two? Yeah. Negative what? 0.07? I think you probably got these two. You couldn't have put this order. What? Okay. a couple of those, like, just flip to the back. I don't want to move on quite yet. So I'm going to say find each p-value. And reject or don't HO. So you're going to decide. Number one, let's say HA was mu is less than whatever. T comes out to negative 2.1. N is 30. Alpha is 0.05. Find the p-value and tell me if you would reject HO or fail to reject HO. To me, this is the hardest part of all this stuff. It's like the p-value, checking whether it's like what we're going to do with it. So I don't really like think about it as the rules I'm writing out. Like if it's this, you do this. I just kind of sketch the t value. So if t is negative. T is the number of standard deviations per hour away from the middle. So if it's negative, are you above or below the mean? You're below. So you're somewhere over there. And the p-value finds you go toward the tail. So I want this area over here. What's the value? What number is way over here on the left hand side? Negative 99999. And I want to go up until where? Negative 2.1. So that's the order you put them in. I just got to think about it left or right. You kind of think about like, okay, because I just gave you these rules, like if it's less than, do this, and it's greater than, you do this. But to me, it's easier to just run left to right. So I'm going to go negative 9999, negative 2.1, 29, because that's one less than the sample size. And 0.0223. Okay. So is the p-value less than or greater than alpha? Less than. So do we reject or fail to reject HO? Reject. Because this is essentially the probability that they're telling the truth. It's very low. Lower. Let's say mu is greater than. T is 1.8. N equals 50. And alpha equals 0.1. So find the p-value and tell me whether we should reject or not. Trying to make it not reject. I failed to reject. So again, I don't think about like the if this and this. I'm just gonna draw it out, and my t value 1.8 is positive, is way over here, and I always want to go toward the table. So what number is way over here on the right? 999 or infinity. So I want to go from 1.8 to infinity. 1.8 goes here, 999 goes there, and I got 0.039. And then 0.039 is less than alpha. So 0.039 is less than my 0.10. So I would then reject. Questions on those two? Go through this again. Why do this? What's going on here? Okay. All right, go back to the front page. Because you get this situation where it's mu is not equal to. If mu is not equal to, cut your p-value, or sorry, cut your alpha in half. Before you compare. I'll show you why. So we're saying mu is not equal to. So like I'm not saying above or below. I'm just saying different. You tell me you throw the discus. Otherwise, not allowed to do. What's that like? What's your average throw? 80 kilometers. So he says 80 feet, and I'm like, I don't know if you're like, if that's too high or too low. I'm just saying it's not 80. So I'm kind of giving myself like it could go either way. So whatever alpha, let's say alpha was 0.05, it gets split, and you put like half of it over here, and half of it over here. So if alpha equals 0.05, you get that whole 0.05, but you got to put it on each side. So if it's like too far away either way, you would reject their claim. So it's the same idea, but we just have to cut alpha in half. So you would say TCDF. T is positive, so T is over here somewhere. And I always want to go toward the tail. So if my T is over here and my tail is over here, doesn't that make my low the T and the high the 999? And then the degrees of freedom. So this is just like the greater than one so far, right? We're going to the tail, we're going above. Let's try an example. Let's say HA's mu is not equal, and T is 1.5, N is 30, alpha is 0.10. So let's find the p-value and try to make a decision. If it's further into the tail, you reject. So in this case, if the p-value is less than 0.025. This is probably, my guess is pretty tough right now to understand. Because people, I don't know. You're saying yes. Let's process. I'm aware that this is like overwhelming for a lot of people right now. We'll get there. So we would type in here TCDF. I've got a positive T value, and I want to always go to the tail, so I want to go above it. So I want to go to 999. Degrees of freedom is 29. This is perfect. This is exactly what the APS would do. So they would give you this 0.07, and alpha is 0.10. So then they would say, do I reject H naught, or do I fail to reject? So you're tempted, maybe, I don't know, to say 0.07 is less than 0.10, so I reject. But that would be wrong. Because in this case, it's a double-sided test. So this alpha needs to be split in half. So what is alpha really? It's 0.05, so now is my p-value lower? not. So would I reject or fail to reject? I would fail to reject. So since p-value is greater than alpha, I failed to reject. But like if you notice what happened, if I forgot to cut it in half, the p-value was smaller. When I remember to cut it in half, I'm sorry. Yeah, when I remember to cut it in half, the p-value was bigger. And that's how they trap you. They'll try to get you to forget to cut it in half and trap you into one thing. But if you do remember it, we'll practice it. Don't forget.
So when you said further into the deal is reject?
Yeah. So this p-value is quite a, like this is less into the tail than this is. 0.05. It's like the area. So this area is 0.05. And that's 0.07. So we're not. 0.05 is here. It's like 5% of the graph. 0.07 is here. It's like you have to go further out to capture more of the graph. So you're not as far.
Yeah.
Right. We're getting there, little by little. Let's just try an example. TCDF, if T is negative, so if T is negative, which side of the graph am I on? The left. And I want to go to the tail. So do I want to go more left or to the right? I want to go more left. So if I'm on the left, I want to go to the tail. I want to go more left to find this area over here. So if I'm looking at this shape, what's the left-hand boundary? The right-hand boundary is T, and then you put your DF. That equals your p-value. So if I give you an example here, HA is mu is not equal to, which as soon as I see that, I have to remember that the alpha now has to apply to both sides. So whatever that alpha is, I gotta cut it in half. Look, half it over here, half it over here. So let's say HA is mu is not equal. Let's say T is -2. Let's say N is 20. And alpha is 0.06. Cool. I don't think I've ever seen this before. Let's change alpha to 0.05. Anybody find the p-value already?
Yeah.
It was 0.03. So when you cut it in half, it was like on it. Which I don't even really know what you would do. I don't know what you do this time. So let's just fix it. Let's just change it. So alpha's 0.05 now. So I would say TCDF. I'm on the left side of the graph, and I want to go more left. I want to go into the tail. So I want to go all the way to -9, -2, 19, and I got 0.03. And then I got scared because that was exactly half of 0.06. So if I forget to cut the alpha in half, what would I do? Reject or fail to reject? I would reject, because if I forget to cut the alpha in half, isn't this smaller than alpha? But if I remember to compare it, I would actually reject. So since p-value, you can do it like this. Since p-value is less than alpha divided by 2. Wait, no, it's not. Since p-value is greater than alpha divided by 2, we fail to reject h. We're going to keep going. I want you to know I'm aware that this is confusing. We're going to fix it. I'm not just like blowing past. Like, okay, you guys are good. Other questions I can answer at this point? Okay. This is a fairly simple one, and then I'm going to get you guys working on some of your own stuff. So, statistical significance. If we reject alpha, or if we reject HO, then the data is statistically significant. Statistically significant basically means I'm calling you a liar. So Evan says he throws 80 feet. He's 81 feet. That's not like far enough away for me to call him a liar. That's not statistically significantly different. If I go and he throws like 40 feet, that will be significantly different. So if the p-value is smaller than alpha, we say the data is significant and we reject. Statistically significant means reject. Let me answer these questions. Yeah.
How like far apart does it have to be in order for you to reject it?
Just low.
But like how you're saying 81. So would you do like if you threw 82, would you still would you reject it?
So, no, that, okay, this, can I like talk about that for a second? So, Evan says he throws 80 feet. Right? It's not 80 yards, right? 80 feet. So, he goes and throws, he throws 79 feet. That p-value, you're going to get more of an answer than you bargained for. He says 80. I go watch him throw, and he throws 79. Well, the p-value would go to the tail. So his p-value would be darn near 0.5, because it's almost halfway to the graph. So his p-value there would be like, let's say 0.4. So if your alpha is like 0.05, is this smaller? It's not smaller, so you wouldn't reject. Because it's so close to the middle. Well, when I go watch him throw, and he throws like 42, that's really freaking far away from the middle. So my p-value, which is this part here, is going to be super tiny. So maybe now it's like 0.001. So like it's a cutoff point, right? So at 80 I might reject, at 79, or 80 I wouldn't reject, at 79 I wouldn't reject, at 78 I wouldn't reject, at 77. But at some point I cross through that threshold and I get too far away. So that's what the math is for. Like I can't look at it and say 81 is yes or no. But that's like how we're trying to make a decision. Well, alright, try those two right there. If you feel lost right now, don't freak out. It'll be okay. Statistically significant means we reject.
How do you know, like, let's say you're on an experiment, and you set your own alpha value, how do you know how far set it? So you said generation falsely rejecting is not right.
So it depends on like what level of accuracy you're looking for. So you kind of said like if I want to be, you know, if it's off by a teeny tiny bit, I want to know and I would reject. Like say I'm fitting like airplane parts, you know, like I gotta have a pretty giant rejection zone because it has to be super precise. But something else I might have more flexibility. So it just depends on like your own. You're kind of designing that your own. Okay, so is the p-value statistically significant in this situation? Statistically significant means you reject, right? Well, in this situation, would you reject? No. Why not? Because the p-value is bigger. So if I'm not rejecting, is it statistically significant? If alpha's 0.05? Would. It is statistically significant values low. Alright, I want you to try the next three. This might be, I'm not sure how it's going to go. We'll see. It might be hard. I'll put the answers up, I'll walk around and help, and we'll try to figure it all out. There are better ways to write these conclusions, but we're not quite getting there yet. I'm not worried about that yet. Maybe tomorrow. Point. Okay. I'll fix that in a second. Logan pointed out to me that I gave you problems that are impossible to solve. Let's say n is 30 for everything. Thank you, Logan. Quick reminder, because everyone freaks out when this happens. What does this mean? Times out of negative chord, so you move the decimal place 4 places to the left. And at that point, you can just say 0. You can just round to 0 because it's so small. Alright, so there's those answers of my work, and I'm sure there's questions that we want to cover. So look at my answers yet. They're stupid, they're wrong. That was this one. Thank you, bye. Jeez. So I don't know. I need some feedback. First of all, there's a question. Where'd you get this? Why'd you get this? This number go here. So give me like thumbs up. This is great. I got no problems. Thumbs down. I don't have a freaking clue what you're talking about, or like sideways. Kind of. Okay. All right. Let's do this. There's a con section. Finding p values. Let's get to work on that. Like, it's a good check so you know what we're doing.